Let's talk about waves and interference. We can have multiple waves exist in the same area together, and when that happens, we have a few different options for what they do, how they interact with each other. We could either have those waves constructively interfere with one another, or they could destructively interfere with one another. And what determines which one of those they do is whether or not they are in phase or out of phase or somewhere in between with each other. What we mean by that is if we have two waves, like you can see here, so we have a wave right here where we have the peak, and then it goes down to the crest, and then comes back up to the peak again, and we have a second wave, and the peaks and crests of the wave are perfectly lined up with one another. This is what we would call in phase, because the points on the two waves are together, essentially. They're the same point for one wave is at the same point in the wave for the other one. So they are in phase together. When we have waves like this, where they're in phase with one another, when they interfere with one another, they constructively interfere. Because their peaks are together, their low points are together, the midpoints are together, everything is together. Everything essentially gets added together. And so the amplitude of the wave becomes greater. Now, notice here that I'm not saying that we are changing the wavelength. We are not changing the frequency. None of that changes. The only thing that changes is the overall strength of the wave. The amplitude of the wave changes. So the wave becomes bigger. It has more energy, but the frequency and the wavelength do not change. Those don't change when we have constructive interference. If, on the other hand, we have waves that are exactly out of phase, so down here we have the peak of this wave is at the crest of this one, the low point of this one, then they are going to completely cancel each other out. When we add these two waves together, as you can see here, these are on exact opposites as well, everything cancels out, so we get destructive interference. The two waves cancel each other so that we get no wave at all, essentially. So that is destructive interference. So in phase interference is constructive, whereas out of phase interference is destructive. So waves are going to exhibit another unique characteristic. When you have traveling waves and they encounter an obstacle or an opening in a barrier that is about the same size as the wavelength of that wave, then they will bend around that. And so this is, again, either an obstacle or an opening that's about the same size as the wavelength itself. This is what we call diffraction. Light is able to diffract through two slits that are separated by a distance comparable to the wavelength, and when it does this, we get what's called an interference pattern out the other side of those two slits. And this is something that only light is able to do. Only things, well, I shouldn't say only light, only waves are able to do this. Any kind of wave can diffract through a slit, and then out the other side you get more waves, but they come out of that slit in this kind of cone-shaped pattern. And this is true for any wave. Like I said, if you've ever been to the ocean or a bay of some kind, and there was an opening, like maybe between two big rocks or something like that, and as the waves were coming in, the waves would go through that little opening. The wave that would come through the opening would not be just a straight line like the waves that were coming into the opening beforehand. Instead, that wave, as it comes through that opening, bends around. It bends around the barrier, giving us this cone-shaped wave out the other side. And so this wave, while it was straight beforehand, when it comes through, it now has this kind of curved wave pattern coming out the other side. And so any wave is going to do this, and only waves will do this. Particles do not do this. So if you shoot particles at a barrier like this, where you have, the walls here, the particles that hit the wall just kind of, they just kind of hit it and stop. They're not going to move forward. And the particles that go through the slit just keep going. They didn't hit anything. Why do they care that they went through an opening? As far as they know, nothing happened. And so they just keep going forward. So waves bend around small openings like this that are comparable to the size of their wavelength. If the wave was relatively small and this barrier was huge, or the opening in the barrier was huge, well then yeah, we wouldn't really see any diffraction. It does have to be comparable to the size of the wavelength. The interesting thing though is that, as we mentioned in the last one here, if we have two slits instead of just one, so we have light that's coming in here, it goes through the two slits in the barrier. Now we have two of these cone-shaped sources of light that are moving through space here as the light travels. And as that continues to go, so both of those continue to propagate out, and I know I'm not drawing that perfectly, but as they continue to move forward, the two waves are going to start interfering with one another, because you can see here they're starting to overlap at different points. And so because the two waves start to overlap and they start to interfere with each other, there's going to be certain points where the interference is constructive and certain points where the interference is destructive. So where we have constructive interference, we're going to see bright points, because the two sources of light are adding together to give us an even brighter light, and at certain points they will add together and cancel out. So we will have dark points in between. So this pattern of light, dark, light, dark, light, dark is what we call a diffraction pattern. And again, only waves can do this. And we're going to come back to this later on in the chapter when we're actually trying to figure out, is something behaving like a wave or is something behaving like a particle? So only waves are able to do this. Only waves can travel through slits like this, spread out, essentially get bent around the opening, and form these new cone-shaped waves, which will then have interference pattern, diffraction pattern, as we call it. So keep this in mind as we move forward, because we'll come back to that diffraction pattern later. But real quick here, I just want to talk about Rayleigh scattering and why the sky is blue. This is not something that I'm going to test you over on the exam, but it is kind of a fun side topic when it comes to light and the different frequencies and wavelengths of light. You've probably thought at some point or wondered why the sky is blue and why sunsets are red. And the reason for this is what we call Rayleigh scattering. This is why actually both of those things are caused by the same effect. So light rays are scattered by particles in the air. So we have a whole bunch of particles in the air, what we'd like to call the atmosphere. So it's nitrogen, oxygen, water, other things like that that's in the air. And as light comes in, it might hit one of those particles and just kind of go woo and get deflected off in a different direction. It's just completely random which direction it gets deflected in. But light could come in, hit a particle, and get bounced off in some other direction. That is scattering. The amount of scattering that takes place is determined by how large the particles are and the size of the wavelength. In general, if you have larger particles, you get more scattering, and this should make sense because if the particles are bigger, there's a higher chance the light's going to hit them. So larger particles give greater scattering. But more important for the color of the sky is that the shorter the wavelength, the greater the scattering. So shorter wavelength light scatters more. So blue light scatters more than red light does. The first one here explains why it's very difficult to see in fog, by the way, because when you're driving through fog, the particles of water in the air are actually quite large. They're not large enough for gravity to pull them out of the air. It's what we call a colloid, where you have very large particles, but not so large that gravity can pull them out. But they're large enough that you get a whole bunch of scattering. And so it's just very difficult to see because the light's just being scattered everywhere. But anyway, we are more concerned with the second one there. Blue light scatters more than red. And so if you are standing here, and it's the middle of the day, so the sun is right above you, the light that you see when you look up into the sky is going to be a mixture of all the colors coming from the sun. But if you, and actually let me write that again slightly differently. If you look directly up, which I should not suggest, don't look directly at the sun. But in that case, you would just be seeing all the colors coming from the sun. But if you look away from the sun, so if you just look at the sky, so not directly at the sun, just up at the sky, there's no source of light from this direction. The sun is here. If you're seeing light coming from this direction, the only way that light is going to come at you from this direction is if light came from the sun over here and scattered down towards you. Because again, there's no other source of light here. Any light that you see coming from this direction had to have come from the sun first and bounced off of something to come back towards you. And that is going to be disproportionately the blues and the greens and the purples, because those are higher frequency, lower wavelength light, the light that scatters more. And so when you're looking over here, what you're going to see is the light that has been scattered, which is again disproportionately blue light. If, on the other hand, you're over here, so you are at sunset or sunrise, and so the sun is way off in the distance, there's atmosphere. Again, I know this is not to scale, but the atmosphere is covering the Earth, and the sunlight has to travel a lot farther through the atmosphere to get to you here than it does to get to this guy. And so because the sunlight has to travel through so much atmosphere before it gets to you, the blues and the greens and the purples scatter away to where most of the light that reaches your eyes are the longer wavelength light that doesn't scatter as much. So the reds and the oranges and the pinks, things like that. And so at sunset and sunrise, the reason that the sky is red, orange, yellow, pink is because that light doesn't scatter as much, and so more of those colors reach your eyes. Whereas if you're in the middle of the day and you're looking up at the sky, the light that is scattered down into your eyes is mostly the blues and the greens and the purples. So then that might leave you with the question, well, wait a second, why isn't the sky violet then? Since violet light is even shorter wavelength than blue light, the reason for that is the sun does not give off all light evenly. Solar radiation is a spectrum of light. And if you notice here, this region is the visible light. And so the stuff down here is actually the blue and the purple and the greens. And right at the edge of visible, which is where the purple light would be, there's less. The sun actually gives off less purple light than it does blue. It gives off more blue and green than it does purple. And so just because the sun doesn't give off everything evenly, the sky is not purple. Personally, I kind of think it'd be cool if the sky was purple. But that's just because I like purple more than blue. So that is why our sky is blue during the day, reddish orange at sunset and sunrise, and why the sky is not purple. Alright, so we'll pick up in the next video talking about the strange things that happen physics and in chemistry that could not be explained using classical mechanics, and how quantum mechanics was birthed into existence through these strange phenomena. So we'll pick up there next time.